An experiment here. So we have a long straight wire. Now, assuming current passes through the wire, we see that if there are iron filings spread all over the surface of this sheet, which is near the vicinity of the long straight wire, we see a formation, a pattern that looks like this. The iron filings will try to orient itself such that it is circulating around the long wire, such that we can show that, or we can see that if we use a right hand notation, if the current that is passing parallel through the wire is pointed by your thumb, okay, in this case it is upward, then your fingers will curl in the direction of the magnetic field, and as you can see, the magnetic field is quite circular. That's why the iron filings will try to follow the circumference of the circle, and it's quite circular. It's quite rotating around, or it's circling around the long straight wire. Now here's another experiment. So assuming we have a compass here, and this is just a wire, and we have a battery that will supply the potential for the current to flow. This is the first scenario. We have the positive and negative side, and if you try to connect that from the initial, we have the undeflected arrow, which is designated by this point. It's red. We see that it goes to the right side after we connect it. Okay, so here we see that the magnetic field is generated when the charges are moving through the wire. And there's a bonus, since we know that charges from our previous lectures has a polarity which is positive and negative. What will happen if we switch the wire such that the red is now on top and the black is on the bottom, which means that this is positive and this is negative? We see now that the charges will flow but in the opposite direction. That's why the deflection is towards the left. Okay, effectively we have something like a south and a north. We know that the needle, this red, the point that is colored red in the needle is pointing towards the north, so effectively we have a south to north. Okay, so a magnetic field is effectively generated if an electric current passes through a wire. Now, what is the relationship, or how do we establish a relationship between the magnetic field, current? We'll see in the next slide. Okay, so here we have the data generated from the experiment. We have a magnetic field, which normally we could use a magnetic field sensor in order to determine the magnitude. Here it is in millitesla, and we have a current. Of course, we can adjust the current of the source. We can supply, instead of one battery, we could have a couple of batteries, so that we can try to increase the current, or we can have a separate power supply such that we can vary the current. And we have found out that in this, from the graph, that the magnetic field is directly proportional to the current. Look at the correlation coefficient, 0.99. It's really indeed a line, so we get the idea that the magnetic field is proportional to the current. Another thing is, if we try to move the magnetic field sensor or a sensing device away from the wire, which has a current that's flowing in it, we see that the magnetic field decreases as our distance, or our radial displacement from the source, or the from the wire increases. So as the distance increases, we see a decrease in the magnitude of the magnetic field B. Okay, and if we try to use a correlation, which is 0.98, we see that the equation is inversely proportional to the magnetic field. Specifically, it is inversely proportional with respect to the distance from the long straight wire. So here, we establish the relationship that the magnetic field B will depend naturally on the current I and geometry and distance. It's inversely proportional to R. Now, we can define that the constant of proportionality mu O to be the permeability of free space, equivalent to 4 pi times 10 to the negative 7. T stands for Tesla, M for meter, and A for ampere. Okay, so that is the working relation. We try to integrate that with respect to a unit vector R, which designates the distance. Let's try to examine this more on the next slide. So again, the equation is written here, and it is a Biot Savart equation. The Biot Savart equation is nonetheless a equation which relates the length of a segment, let's say infinitesimal length within the wire, okay, designated as this distance from this red arrow to up to the adjacent red arrow. So that's the length of the segment. The radial distance is, the radial direction is stipulated by the purple arrow, which is directed to point P. Point P is our that's where we want to measure the magnetic field B. Okay, so of course that is inversely proportional to the distance again, and we sum all over the segment S. Okay, so we have a collection of infinitesimal segments, then we add them all up to come up with the finite segment, or the total length of the wire, for example. So that's the formula. Okay, and remember the proportionality is mu sub O. Okay, so regarding the units, I is again in ampere, and as I have said, the permeability is Tesla meter per ampere, and the length is given in meter, indicated by the purple, and the distance is meter squared. Okay, so effectively the meter cancels out, the ampere cancels out, and the resulting unit is Tesla, T, for the magnetic field vector B. Okay, so let's try to have an example in order for us to understand what is essentially inside the integral, with this the infinitesimal length we cross multiply to the radial unit vector R, and then it's divided by R squared. Okay, so we have an example here, a long straight wire. So here in the long straight wire, again we have this, the point of consideration is point P, then we want to evaluate the magnetic field B at that region. Now this long segment of wire, we have it from negative A to A, so we can write that as the limits of integration, negative A to A. Okay, now if we try to cross S and R, we see that the R is in this direction, and the infinitesimal length, which is dl, if we try to cross that, so again, so we have the cross product to be sine of the angle. Okay, so sine of the angle is just simply x, or the opposite side, over the hypotenuse, which is r. Now the thing is, x over r for the cross product s and r hat, but there's another r squared at the bottom. So what's the value for r squared? So that is x squared plus y squared raised to 1. If we combine that with x over r, then we can see that the denominator the quantity x squared plus y squared, it should be raised to 1 plus 1 half, 1 plus 0.5, or 1 and a half, 3 over 2. Now we can use a trigonometric substitution in order for us to show that the resulting magnetic field B is mu y over 4 pi 2a over the product of xn squared of x squared plus a squared. We will not go on to the details of the calculation. We can look into a table of integrals in order to evaluate it, such that, well, so that we can see more of the physics involved, not the mathematical derivation. Well, we can try to approximate this, assuming that our wire is essentially long, such that our A is considered to be infinite. So what matters in the radical is a squared, and we can what will happen to the a squared after we take the square root of that. It's just a, and we cancel with the numerator, so a will cancel with the a, and we are left with mu I over 2 over 4 is 2 pi, and we replace the x simply by the radial distance from the center of the long straight wire. Okay, so replace x by r, and we have the formula mu I over 2 pi r for the magnetic field of a long straight wire. Okay, so we have a problem here. We have problem. We want to simulate the magnetic field at point K given these two wires. Okay, the current in the first wire is directed away from me, and the current in the second wire is directed towards me, and both of them has an current of around 10 ampere. Okay, and the surrounding environment is air, and again we want to compute for the magnetic field at point K. Now, before doing the longhand solution of this, I want to make a computer simulation for us to see better what the magnetic field looks like and what's the resulting value of the field at point K. And we can use a program. The program is called Quick Field. It's a student edition. You can download that, and we can have it working here in our laptops. We have already performed the setup, and here we have the first conductor, which is I1, and the second conductor as I2, and our point of consideration is at K. So here we could specify a boundary. So the boundary is essentially a circle. Okay, we assign the magnetic potential to be 0, then the air inside has a permeability of 1. Okay, so the value of the current is 10, and as we all know, if we use finite element analysis, we have to generate a mesh. So the mesh is automatically generated by the program, and then we try to compute now or simulate the magnetic field. Okay, and it's done. So our point of the point K is situated 0.5 meters above the first conductor, and the value is around 3.4 and negative 2 microtesla. Now, roughly, the magnetic field lines are not that smooth, so we need to refine the mesh in order for us to have a better approximation of the value or the magnetic field at K. Okay, and I have done that. Now here at point K, the value is 3.2 and negative 1.6. Now we can say that the value we obtained here is already correct, since the magnetic field lines are relatively smooth. Okay, it's circulating around the first conductor and the second conductor. Now, so That's how we simulate it. Now we want to do the longhand solution. Okay. Now, due to the first conductor that is pointing away from me, so we can use our thumb, so we can try to point that away or towards the away from me or towards the monitor. So we can see that my fingers curl towards the right, so that's B1. Okay. Similarly, for I2, we can use our thumb and point it outward the monitor towards me, and then my fingers will try to curl at the direction of the magnetic field. As you can see, that is left downward. Okay, so that's B2, left downward. Now that we have properly identified B1 and B2, we can use the superposition principle in order to find the total magnetic field at K. So again, we have I've written the formula B equals MUI over 2 pi r. If we multiply the numerator and the denominator by 2, so mu over 4 pi is 10 to the negative 7, so we have the 2 there, and from the given, the current is 10 amps. Divide by our distance, which is around 0.5 meter, so we need to convert 50 centimeter to meter, and the result is 4 microtesla. And as I have discussed before, B1 is directed towards the right. It has no y component, it only has an x component of 4. Now, since we know that, we can apply that in the second wire. So again, that's 10 to the negative 7 multiplied by 2, and the current, which is 10. Now this time, we want to know the distance from K to the second wire, and that is simply solved by Pythagorean, which is the square root of 0.5 square and 1 square. Turns out that that's 1.1. So at B2, that is 1.8 microtesla. But since our B2 is directed left downwards, we have to use sine and cosine function to determine the x and y components. Now for the x component, we use sine 26.6, and for y component, we use cosine 26.6 degrees. Okay, so that's the complement of 63.4 degrees. Okay, so the resulting value is 0.8 and negative 1.6 microtesla. Now here's the fun part. We now try to find the x and y component of the magnetic field at point K. If we add B1 and B2 corresponding to the x and y components, of course we know that x is 4 minus 0.8, so that's 3.2, and for the y it's just negative 1.6. So again, our value is correct. From the simulation up to the longhand, they are in agreement. It's 3.2 and negative 1.6. As you can see in the simulator, it is truly 3.2 and negative 1.6. So that ends our simple discussion with respect to using a Biot and Savart equation. And here are the